Welcome to Lecture 12 of Microeconomic Analysis 1 with me, Dr. Craig Webb. In today's lecture, we will be looking at long-run production. So we'll be developing tools using the long-run production function. We will look at isoquants, develop the idea of the marginal rate of technical substitution. We'll look at something called the elasticity of substitution. And finally, we will have a look at a concept called returns to scale. So let's get started. In our model of production, we assume that the firm uses two factors of production, labour denoted capital L and capital denoted capital K. The firm uses these two inputs to produce an output which can then be sold in the market. In the long run, we assume the firm can vary all inputs, so the firm can now freely choose different quantities of labour and different quantities of capital in order to produce in the most efficient way. To describe the relationship between different factor combinations of labour and capital and the firm's output, we use the mathematical device of a long-run production function. Here I've written Q, which is output, is equal to a function f of labour and capital. Now, to produce diagrams and represent this production function graphically, notice that there are three dimensions here: output, labour and capital. And we could, in principle, produce three-dimensional diagrams. However, this is rather tricky, so we're going to use a similar device that we used when studying utility functions. Instead of drawing the three-dimensional representation of the function, we're going to look at the level sets of these functions, and we give them a specific name, isoquants. So let's develop this idea now. To represent different combinations of labour and capital, we're going to use a similar idea that we used in consumer theory, where we constructed a diagram of commodity space. This time, we're going to draw a picture that we will call factor space. So, for each different factor combination, so a particular factor combination is a pair with some amount of labour and some amount of capital, L and K. Similar to a bundle in consumer theory, we'll call this a factor combination. And to represent this diagrammatically, here I've produced a diagram with labour on the horizontal axis and capital on the vertical axis. So all of the different combinations of labour and capital that are possible are represented by the non-negative orthont of the plane. Here I've picked a particular point in this space, and this is a two-dimensional point. It has L units of labour and K units of capital. Now, an isoquant, the term iso meaning single, so single quantity, an isoquant is a curve or a line that connects all the different combinations of labour and capital that yield the same output. So one way of denoting this would be as a set, so I've used curly braces here, a set of all the different LK factor combinations, with the rule that, or the property that, if we plug these combinations into our long-run production function, we get the same number equal to a constant C. Graphically, I've drawn two isoquants here. The lowest of these isoquants, we can see all of the different combinations of L and K, where if I plug these into the long-run production function, I get output Q1. On the higher isoquant, we get this curve connecting all of the different combinations of L and K that produce the same level of output, and this is equal to Q2. So this is very similar to an indifference curve. Mathematically, it's a level set of the long-run production function. These are level sets of that long-run production function. There is a slight difference in interpretation here. Remember that with utility numbers, the actual numbers had no cardinal significance, by which I mean if we double utility, that really doesn't mean very much, apart from saying, well, we are now in a more preferred position. When we're talking about output, if I am doubling output, then that really does mean something very concrete. It means exactly that output is twice what it was before. So isoquants have cardinal significance, which is slightly different to the indifference curve case. This will play a role as we discuss mathematical properties such as homogeneity later on. As we work with isoquants, we will make several basic assumptions about their properties. So first and foremost, we will assume that the further an isoquant from the origin, the greater the level of output. This is equivalent to saying that if I increase labour and capital, then my output goes up. So we have a monotonically increasing long-run production function. This is something we will assume in our diagrams. We will also assume some basic properties such as isoquants do not cross and isoquants slope downwards, and that isoquants are perfectly thin, so they have zero width. Further, we will assume that isoquants are strictly convex. This is a typical assumption, although there are other cases, but the assumption of strict convexity of these curves has a specific economic interpretation, which we'll discuss next. As we move along an isoquant, we are exchanging capital for labour, and because we're talking about an isoquant, we are maintaining a constant level of output. Therefore, the slope of an isoquant is going to tell us the rate at which the firm can exchange capital for labour, or indeed any other factor for any other factor, whilst maintaining the same level of output. We give this a name, the marginal rate of technical substitution. So we'll denote it MRTS, the derivative of capital with respect to labour, and we'll show next that this is equal to a negative ratio of marginal products. So it's minus the marginal product of labour divided by the marginal product of capital. This is something we will prove shortly. If I look at this diagram, graphically, the marginal rate of technical substitution at the point LK is the slope of the blue line that is tangent to the isoquant. It's telling me the rate at which I can exchange capital for labour whilst maintaining a constant level of output. Now, as we assume isoquants are strictly convex, then for low levels of labour, these are very steep, and as labour increases, the isoquant becomes flatter and flatter. This essentially means we are assuming a diminishing marginal rate of technical substitution. Now, as with the marginal rate of substitution in consumer theory, the marginal rate of technical substitution, in this course we think of it as a negative number. And when we say diminishing marginal rate of technical substitution, we mean it's getting smaller in absolute size. So the slope is becoming less negative. If you read different textbooks, you have to be quite careful because sometimes marginal rates of technical substitution, marginal rates of substitution in consumer theory, and so on, are sometimes taken to be positive numbers rather than negative numbers. This is not too difficult, but just make sure you follow what that textbook is saying carefully, and in this course, we'll think of it as a negative number. So let's move over to paper now, and we will prove that marginal rate of technical substitution is equal to this ratio of marginal products. And let's consider an example. Let's have a go at calculating the marginal rate of technical substitution for our well-known Cobb-Douglas long-run production function. Okay, so let's have a look at the marginal rate of technical substitution first, and then we'll focus on the Cobb-Douglas long-run production function as an example. Okay, so if we start with a general long-run production function, so output Q is a function of labour and capital. Okay, So let's take the total differential of this. So we've seen this before. We're essentially saying, so this is quite intuitive, the change in output, well, output can be changed by two things. It changes when we change labour, and it changes because we change capital. And each of these changes are taking effect through the production function. So this change in output if I change labour by dL, then this changes output, and this is the partial derivative of the production function with respect to labour. Okay, so how much do I change labour? How much does that change in labour change output is part of the total contribution to the change in output. And I add to this a similar expression for capital, so the partial derivative of the long-run production function with respect to capital multiplied by how much we're changing capital. So this is called a total differential, okay? And of course we gave these particular partial derivatives names. We called this the marginal product of labour multiplied by dL plus, and this partial derivative of f with respect to capital we called the marginal product of capital. Okay, so that was from the previous lecture. So this is an expression for the total differential of output. So let's think about an isoquant now. So what happens on an isoquant is that it's all of the different combinations of labour and capital that produce the same amount. So one way of saying that is that output is constant along an isoquant. Another way of saying it's constant is to say that the change in output equals 0. So this expression, change in output equals 0, is true on any given isoquant. Okay? And this is the same as saying that this expression here equals 0, marginal product of labour dL plus marginal product of capital multiplied by dk is equal to 0. So it's not always equal to 0, but on an isoquant, it is equal to 0. Okay? Now, if we rearrange this expression, we can get the slope of the isoquant, which is dk over dl, which is minus mpl over mpk. Okay, so this was from the slide that the slope of an isoquant, or the derivative of k with respect to L, is equal to a ratio of marginal products. Okay, so we've seen something very similar when we did marginal rate of substitution. This is what we called the marginal rate of technical substitution. Okay, so let's look at the Cobb-Douglas long-run production function. So the Cobb-Douglas example was where output Q is equal to some positive number A multiplied by L to the power alpha and multiplied by capital K to the power beta. Okay? So let's calculate the marginal rate of technical substitution. Let's find an expression for this for the Cobb-Douglas case. So let's start by calculating the marginal products. So marginal product of labour in this case would be the partial derivative of this with respect to L. So I'm treating capital K as a constant. So if I take the derivative of this expression, treating A and K as constants, then I get alpha A L to the power alpha minus 1 multiplied by K to the power beta. Okay? And if I do the same for capital, the marginal product of capital in this case would be, well, then I'm taking L and assuming it to be constant and treating K as the only variable. So I get beta times A L to the power alpha K to the power beta minus 1. Okay, so these are expressions for the marginal products. Now the marginal rate of technical substitution, which is simply the ratio of these. So with a minus sign in front, so it's minus, let's write this out fully, alpha times a L to the power alpha minus 1 multiplied by k to the power beta, all divided by beta multiplied by a multiplied by L to the power alpha multiplied by k to the beta minus 1. So clearly there's some things that would cancel out. I could cancel these a's immediately. And if we look, I have alpha copies of L on the bottom and only alpha minus 1 on top. So there's one extra copy of L on the bottom. And with k, there are beta copies on the top and beta minus 1 of them on the bottom. So there is one extra copy on top. So cancelling these out, I get marginal rate of technical substitution is alpha over beta multiplied by k over L. Okay, so it's a rather simple expression. So that's perhaps the simplest way of doing this. There is another way. So another way of doing this would be to, for example, if I just write down the equation for a particular isoquant. So here I just used a property of an isoquant and then derived this formula. But we could be more specific in this case and say, well, there's an isoquant where A times L to the power alpha times K to the power beta is just equal to some constant. Let's call that Q bar. Okay, so this would be the isoquant, all of the different LK, where output is precisely Q bar. Okay, now remember I'm looking for the derivative of K with respect to L, restricting attention to this isoquant. So if I rearrange this, I could get K by itself. So K is equal to Q bar divided by A times L to the power alpha, and then all of this to the power 1 over beta. Okay, so as an exercise, you could try differentiating K with respect to L. You'd need to use the chain rule, and then at some point you substitute in the fact that Q bar is equal to, the fact that K is equal to this, which appears again. So if you do that as an exercise, you'll find the marginal rate of technical substitution. You can do this because the Cobb-Douglas function, you're able to kind of isolate K by itself. Now, you can't always do that with long-run production functions, but this is a neat way for the Cobb-Douglas case. The marginal rate of technical substitution is telling us how the firm can substitute labour for capital and capital for labour in a way that maintains the same level of output. So graphically, it was the slope of an isoquant at a particular point. Now remember that we assumed that isoquants have a strictly convex shape. That is, we assumed diminishing marginal rate of technical substitution. Now there are many types of convex curves. Clearly, if we have a very curved isoquant, then you could think that the marginal rate of technical substitution is changing very quickly. If, on the other hand, we looked at isoquants that were convex but almost linear, so really not very curved at all, then the marginal rate of technical substitution would not be changing very much along that isoquant. Clearly, the curvature of an isoquant is going to tell us something about how fast this marginal rate of technical substitution is changing. Now, in order to develop a measure for this curvature, we use the notion of elasticity of substitution. This is a rather unusual concept the first time you see it, so let's work through an example just to see what's going on before we introduce the formal definition. So in this diagram, I've drawn 2 points, 2 different factor combinations that I've labelled point A, which has 2 units of labour and 4 units of capital, and point B, which has 5 units of labour and 1 unit of capital. I've drawn an isoquant, so everywhere along this yellow curve, output is equal to Q bar. And at point A and point B, I've drawn these blue lines which are just tangent to the isoquant. So the slope of these blue lines tells us the marginal rate of technical substitution at points A and B. Now, I haven't drawn this precisely accurately, but let's suppose that at point A, the marginal rate of technical substitution is -2. And let's suppose at point B, the marginal rate of technical substitution is -0.4. Let's record these in a table and note that the marginal rate of technical substitution changing from -2 to -0.4 is a reduction of 80%. Okay, so to calculate that 80%, you would take -0.4, deduct -2, and divide by -2, and then multiply it by 100 to get a percentage. So this diagram, going from point A to point B, the marginal rate of technical substitution has decreased in absolute size by 80%. Let's now consider what we call capital-labour ratios. So simply, at any point, I take the units of capital and divide it by the units of labour. What would this mean graphically if I look at point A and I draw a red line back to the origin from that point? Now, if I take the slope of this line, I'm dividing how far it goes in the vertical direction, so how much capital there is, divided by how far it goes in the horizontal direction, how much labour there is. So the slope of this line is K divided by L, which in this case is 4 divided by 2, which is equal to 2. So let's record that in our table. At point A, the capital labour ratio, K divided by L, is equal to 2. I could do the same exercise at point B. Now at point B there is 5 units of labour and 1 unit of capital. So the capital labour ratio, the slope of this red line connecting point B back to the origin, is 1 divided by 5, which is 0.2. So we notice that this, moving from point A to point B, the capital labour ratio has changed from 2 to 0.2. So it's decreased by 90%. So let's introduce the idea of elasticity of substitution. The formal definition of elasticity of substitution is the percentage change of the capital labour ratio divided by the percentage change in the marginal rate of technical substitution. So it's the percentage change in the slope of the red lines in response to percentage changes in the slope of the blue lines. Okay, so graphically that's the idea, and it's telling us essentially a measure of curvature of this. We'll discuss this more in a second. Really, it's a measure of anti-curvature in the sense that the higher this number is, the less curved the isoquant is. Now, in this case, the percentage change in the capital labour ratio was -90%. The percentage change in the marginal rate of technical substitution was -80. So we get an elasticity substitution measure of 1.125. Okay, so I've used here what might be a notion of arc elasticity. I've done this with discrete changes. But of course, when we're developing the idea more formally, we're going to use evaluating this at a point. So we'll use the derivative of the capital labour ratio with respect to the marginal rate of technical substitution, and then multiply this by the marginal rate of technical substitution divided by the capital labour ratio. So we've seen elasticity formulas before. We know how to take the elasticity of y with respect to x. Well, here we're taking the elasticity of K divided by L, with respect to the marginal rate of technical substitution. The lower this elasticity is, the more curved the isoquants are. For instance, if sigma, which we'll use to denote this elasticity of substitution, if sigma is very high, the isoquants are really not very curved at all. And in the limiting case, where sigma is infinite, we're talking about perfectly linear isoquants. So let's use this definition and work through some examples. As a first exercise, I would like you to practice by showing that for the Cobb-Douglas long-run production function, the function f of Lk is equal to a, some constant parameter capital A, multiplied by L to the power alpha, multiplied by K to the power beta, where alpha and beta are positive, show that if you calculate the elasticity of substitution at any point for this function, you always get the same number and it's always precisely equal to 1. Okay, so have a go at that yourself. I won't go through that in the lecture, but please ask questions if you struggle with this in any way. Here's an example that we will go through next. Now this is called, it's another long-run production function, and it's called the constant elasticity of substitution, or the CES production function. So it looks like this. Output Q is equal to, and then we have some constant parameters A and B, and a rho parameter, where it's Q is equal to A times labor L to the power rho, plus B times capital K to the power rho, and then we take all of this and take the expression to the power 1 divided by rho. Okay, so it looks rather unusual the first time you see it, but as you begin to work with it, it feels a little more simple than it looks. In particular, it has this very nice property, which as an exercise we'll show on paper next, that if we calculate the elasticity of substitution for this function, then sigma is precisely equal to 1 divided by 1 minus rho. Now this is just a number, so essentially the elasticity of substitution could be any number for this function, but it has to be constant. Okay, so that's the key idea. This is the particular class of functions for different rho, but this is the class of functions that always exhibit constant elasticity of substitution. We'll prove this on paper next, but you might want to pause the tape and have a go at calculating sigma for this particular function before we go through it. Okay, so let's have a look at this exercise of proving that the constant elasticity of substitution production function, the CES long-run production function, really does exhibit constant elasticity of substitution. Okay, so let's just remind ourselves that the CES production function is as follows. Output Q is equal to, and then we've got A times L to the power rho, this is the Greek letter rho, plus B times K to the power rho, and we take all of this to the power 1 over rho. Okay, so this is the CES long-run production function. And let's remind ourselves what elasticity of substitution is. So we denoted it sigma, and we said it's the elasticity of the capital labor ratio with respect to the marginal rate of technical substitution. Okay, so one way of writing this would be the derivative of the capital labor ratio, K over L, with respect to the marginal rate of technical substitution, and then to make it an elasticity, we multiply it by marginal rate of technical substitution and divide it by that capital labor ratio. Okay, so it looks unusual, but really it's just the elasticity of one thing with respect to another, where we're talking the elasticity of K divided by L with respect to the marginal rate of technical substitution. Okay? Right, so to show that, and we want to show in this case that sigma is equal to 1 over 1 minus rho, okay, which is just a constant number. So the exercise was to prove this. So we need to first get an expression for the marginal rate of technical substitution for this particular production function. So if we remember, the marginal rate of technical substitution was equal to, well, we've shown already that it's equal to a negative of ratio of marginal products. So the marginal product of labour divided by the marginal product of capital with a minus sign. Isoquants slope downwards. So we do it with a minus sign. Some books are different. So let's calculate each of these terms. The marginal product of labour, which is the partial derivative of this with respect to labour. Okay, so we're going to treat capital as constant. Now, to differentiate something like this with respect to L, we're going to use the chain rule, differentiate the outside of the bracket, and then differentiate the inside of the bracket. So we would get 1 over rho, A times L to the power rho, plus b times k to the power rho, all to the power 1 over rho minus 1. Okay? That's the first step, and then we multiply this by the derivative inside this bracket, which would be rho times a times L to the power rho minus 1. Okay? So that's an expression for the marginal product of labour for the CES production function. The marginal product of capital is going to look quite similar. So it's 1 over rho. The first part's identical. The 1 over rho minus 1. And then we multiply by rho times b times k to the power rho minus 1. Okay? So these are the marginal products. They look rather complicated, but when we calculate the marginal rate of technical substitution, an awful lot's going to cancel out because we're going to divide all of this by all of this. And you can see the 1 over rho will cancel out. Everything in this bracket will cancel out. These rows will cancel out. And we'll be left with A over B multiplied by L to the rho minus 1 divided by K to the power rho minus 1. Okay? And we could also write this as A over B. Now we're interested in this capital labour ratio, so maybe we should write it as K over L, which is, and then 1 minus the power rho. Okay? So you can check that this is the same. I've just gathered some terms together and inverted that bracket, which means taking to the power minus 1. Okay, so now we've got this expression. How are we going to calculate this elasticity of substitution term? Well, let's get K over L by itself. So if we rearrange this, we would get K over L is equal to, oh, apologies, this would have a minus sign here because of the, I forgot to include it here. Okay, so we would be minus B over A multiplied by the marginal rate of technical substitution, and then taking everything to the power 1 divided by 1 minus rho. Okay? So this expresses the capital labour ratio in terms of the marginal rate of technical substitution. Okay? Now it might be easier to just, because this, we'll do lots of steps next, just to rewrite this. So let's let small k be K over L, and we'll just write small m for MRTS. Okay? So just replacing these variables, I'm just relabeling them. I'm not doing anything fancy here. we would get little k is equal to minus b over a multiplied by m, little m, all to the power 1 over 1 minus rho. Okay? So now to calculate sigma, I'm going to use this expression and take the derivative of little k with respect to little m, that's the same as this, then multiply it by little m over little k. Okay? So, and now we've got k, it seems to be a power function of m. So we can see already that looks a bit like the constant elasticities we've seen before. But we could work through this example anyway and just actually calculate these derivatives. So if we take the derivative of this with respect to m, what do we get? So we'll differentiate the outside of the bracket followed by the inside. So we would get 1 over 1 minus rho multiplied by minus b over a times m, 1 over 1 minus rho minus 1. Then multiply the inside, differentiate the inside of the bracket with respect to m, would be minus b over a. And then multiply by m and divide by k. Okay? So now we want to tidy this up a bit, and I'll do this quite quickly. So here I've got, I know that k is this expression here, which appears again here, but with an extra minus 1. So if I replace k here where I can, so 1 over 1 minus rho, let's replace this with this expression here with k, and then there's another of these just to the power minus 1. Okay. And then we get b over a, so minus b over a multiplied by m divided by k. Okay. Now if we examine each of these terms, we've got k divided by k, we've got m to the power minus 1 multiplied by m to the power positive 1. We've got minus b to the power minus 1 multiplied by minus b. And we've got 1 over a to the power minus 1 multiplied by a. So this gives our result that sigma is equal to 1 divided by 1 minus rho, where this rho is the power term in the constant elasticity of substitution production function formula. So there we go. That proves that this long-run production function, when we calculate the elasticity of substitution, we get just a single number, 1 divided by 1 minus rho. The final idea we're going to study in this lecture is the concept of returns to scale. Now, returns to scale addresses the question, how much does output change if a firm increases all of its inputs proportionally? So, for example, if a firm is using a certain amount of labour and a certain amount of capital to produce output, what happens to its output when, for example, the firm doubles all of its inputs? To develop this idea, first a mathematical definition is required. We will say a production function, or indeed any function, is homogeneous if there exists a number gamma such that the following equation holds. So here I've got a function f, a production function, and I've multiplied labour and capital both by a positive number x greater than 0. Okay, so I've got f of x times L and x times k. So if x were equal to 2, I'm essentially saying the output from doubling my labour and doubling my capital. Now, if this is equal to the production function f evaluated at Lk, but multiplied by x to the power gamma, where gamma is a constant, then we say the production function is homogeneous. Okay? Now, for any function, we could always find a gamma to make this equation true, the important part for homogeneous functions is that gamma is always the same. Okay, so there is precisely one gamma where this equation holds for all values of x greater than 0 and all values of labour and capital. So multiplying all the inputs by a factor x greater than 0 changes output by a factor x to the power gamma. Okay, so we would also say in this case that this function f is homogeneous of degree gamma. Now suppose, for example, that we had a long-run production function and it was homogeneous of degree gamma equal to 1. So homogeneous of degree 1. What would this mean? Well, it means that if we multiply all of our inputs by the same number, x greater than 0, then our output is multiplied by the same x. For example, if x equals 2, doubling all inputs would lead to double output. This is what we call constant returns to scale. So if we have a homogeneous long-run production function, which is homogeneous of degree 1, then the long-run production function exhibits constant returns to scale. Now, in general, we can think of this parameter as measuring the returns to scale, this gamma parameter, and say that, well, if we have a production function that is homogeneous of degree gamma, then the function f exhibits constant returns to scale if gamma is equal to 1. Then f exhibits increasing returns to scale if gamma is greater than 1, in which case doubling all our inputs leads to more than doubling our output. And f exhibits decreasing returns to scale if gamma is less than 1, in which case doubling all of our inputs would lead to less than doubling of our output. Let's work through an example using the Cobb-Douglas production function to highlight the idea of homogeneous functions and the connection to returns to scale. Okay, so let's look at the Cobb-Douglas long-run production function again. So if we remember the Cobb-Douglas function, f of Lk is equal to a times L to the power alpha multiplied by k to the power beta. Okay, where a, alpha, and beta are positive constants. So we want to show that, first of all, this is a homogeneous function, and we'll establish the degree of homogeneity, and then look at the idea of constant or increasing or decreasing returns to scale. When does that happen? Okay, so if we take any number x, okay, so x is a positive number, and we're going to multiply all of our inputs by the same number. Well, what happens to output? So what I'm asking is, if I take the long-run production function, multiply labour by x, and multiply capital by x, what do I get? Okay, well, essentially I'm just replacing L here with XL, so I would get A multiplied by XL units of labour to the power alpha, multiplied by, multiplied by X times K to the power beta. Okay? And now I can do some cleaning up and write this is equal to, I've got x to the power alpha and x to the power beta. So if I take that out the front, I've got x to the power alpha plus beta. Okay? Multiplied by a, multiplied by L to the power alpha, multiplied by k to the power beta. Now this expression is the same as the output when labour is L and capital is K. So this is equal to x to the power alpha plus beta multiplied by f of Lk. Okay? So if we check the definition of homogeneous functions, we can see that this function is homogeneous of degree alpha plus beta. Okay? So the sum of these powers determines the returns to scale for this function. So for instance, if alpha plus beta equals 1, so if I have alpha here and 1 minus alpha here, then this is saying constant returns to scale. Okay? If I have alpha plus beta is greater than 1, this means increasing returns to scale. And if alpha plus beta is less than 1, then I have decreasing returns to scale. Okay? So that's a simple way of characterizing the returns to scale for the Cobb-Douglas long-run production function family of functions. I simply look at the powers alpha and beta, and I take their sum, and if their sum is equal to 1, greater than 1, or less than 1, then I know that the production function exhibits constant or increasing or decreasing returns to scale. So this completes our study of production for now, and in the next 2 lectures we'll be looking at the firm's costs. Of course, we will use our knowledge of production functions and the ideas developed over the last 2 lectures when analysing the firm's costs. So how much does it cost to produce a certain amount of output is going to depend on the firm's production technology and on some other things which we'll introduce over the next 2 lectures. Of course, it's vital to understand the firm's costs because profit is revenue minus cost, and profit maximization is the ultimate goal of the firm in microeconomics. In the next lecture, we'll focus on short-run costs, and in the final lecture, we'll have a look at the long-run costs case, where we'll look at the firm's cost minimization problem and derive the cost function, the long-run total cost function, using many of the tools that we've developed today and in the last lecture. Lots to look forward to, so I look forward to seeing you next time. But in the meantime, take care.